So we have this LCR circuit where we can vary the frequency of this external source. We have a capacitor and a coil with a internal resistance. We are given that at frequencies omega 1 and omega 2, the current amplitudes are n times less than the resonance amplitude. And we need to find what is the resonance frequency and quality factor of the circuit. So you must be familiar with current versus frequency graph. And you can see at certain frequency you will get the maximum current. That is our resonant frequency. Now it's given at omega 1 and omega 2, we are getting the current to be, maximum current to be the resonant current by n. So here will be omega 1, here will be omega 2. And at both omega 1 and omega 2, we are getting the maximum current, that is n times less than the current we got at resonance. We need to find what is the value of omega naught if omega 1 and omega 2 are known to us, and at omega 1 and omega 2 current is Im by n. So let's start with what is given to us. So at resonance the maximum current Im is Vm by R. So n times less than that is the current at omega 1 and omega 2. So let's write that as Vm by Z. So Z is root of R square plus XL minus XC whole square. So we cancel Vm and we get n square minus 1 R square is equal to omega L minus 1 by omega C whole square. So at this omega 1 and omega 2, this condition satisfies. So of course the root of this equation are omega 1 and omega 2. Now you know the XL varies linearly with frequency and XC will reduce. So XC is inversely proportional to frequency because XC is 1 by omega C and XL is equal to omega L. So XL will vary proportionately with omega and XC will inversely vary. So you can see at omega 1, XC is more than XL. At omega 2, XL is more than XC. And at resonance, XL and XC are equal. So that's why at resonance, this term will become 0. However, we are interested in these 2 points, omega 1 and omega 2. So at omega 1, let's say XC is greater than XL. So if XC is greater than XL, so XC is greater, so this term will become 1 by omega 1C minus omega 1L. So we can remove the square now. So this term will be positive if XC is greater than XL. And if XL is greater than XC, then this term will be positive if we write it as omega 2L minus 1 by omega 2C. So we want to get the term of LC so that we can introduce omega naught here. So you can see that will occur if you subtract the 2 equations. So if you subtract, these 2 terms will get cancelled and what you will get is omega 2 plus omega 1 into L minus omega 2 plus omega 1 by omega 1 omega 2C is equal to 0. Omega 1 plus omega 2 will get cancelled and you will get omega 1 omega 2 is equal to 1 by LC. And we know 1 by LC is omega naught square. So they wanted to know resonance frequency, so that is omega naught, so that is root omega 1 omega 2. So you can kind of imagine if you do root of omega 1 omega 2, you are going to get omega naught. Now in second part, the quality factor. So from 1, that if we just take one of these equations, so let's take this first equation. So from here, I've just rewritten this equation by taking C out. So if you take C out of, I'll just show it to you again. So if you take C out, you will get 1 by omega 1 minus omega 1 into LC. So why we are doing that? So because we know what is LC. So we just saw that LC is 1 by omega naught square and omega naught square we just saw is omega 1 omega 2. So we do that and what we get is RC is equal to 1 by n square root n square minus 1 into 1 by omega 1 minus 1 by omega 2. Now quality factor is this in terms of omega naught C and R. And here we have a term of RC. So that's why we are using this equation. So we have proven this in 4.129. So we put that value here of RC, and omega naught, of course, we can put as omega 1, omega naught square we can put as omega 1, omega 2. So we do that and we simplify, and this will be our answer. All right.